Hi, I'm Dr. Frank Summers of the Space Telescope Science Institute, and welcome to the Hubble National Teach-In. First, we've got a very special guest, NASA Administrator Charles Bolden, who wants to give you his own personal welcome.
Thank you to all the educators, students, scientists, and engineers participating in today's Hubble Teach-In. When we launched this magnificent telescope 25 years ago today, we knew it would be special, but we really had no idea the degree to which it would transform our understanding of the universe and rewrite textbooks. Today, the Hubble Space Telescope continues to provide more data each year than there is in the entire Library of Congress. It's confirmed the presence of black holes in the centers of the galaxy. It made the first observations of the chemical makeup of the atmosphere of a planet orbiting another star. It helped scientists determine that the cosmos is 13.7 billion years old. It provided the first high-resolution maps of the structures of planet-forming disks around stars like our sun. And those are just a few of Hubble's greatest hits. It was my great pleasure to be a part of the crew that brought Hubble to space. Many astronauts since have helped repair it and keep it running, and many talented and dedicated folks on the ground have continued to monitor and manage this magnificent one-of-a-kind telescope. There are nearly endless possibilities for learning from the wonderful data and images that Hubble continues to send us. I applaud the Teach-In for helping to inspire the next generation of scientists and engineers who may someday work on their own great observatory and once again transform humanity's understanding of our place in the universe. I hope you learn a lot today. I also hope your journey with Hubble, the James Webb Space Telescope that launches in just a few years, and all of NASA's missions will continue to inspire you and help you make your own great leaps of discovery.
The public outreach here at STSCI. In particular, I want to give you a welcome from Bonnie Eisenhammer, our Education Program Manager. She's the one on the right in this image. Bonnie and I work very close together. We believe in the scientist-educator partnership, which is what makes our education program so special. We also have a lot of other folks here at the Space Telescope Science Institute. This is one of our group photographs we've taken when the astronauts come to visit. You can see that there are a lot of folks here. And it includes the people that you might normally expect, the astronomers, the engineers, the computer programmers. It also includes the people that you need to run a business, those who'd work in finance, personnel, maintenance. But it also includes some people you might not expect, like writers, artists, and teachers. These are the people that help us get Hubble's discoveries out to the public and out into our education. And I think for us, it teaches a lesson that you don't have to be a PhD astrophysics geek to work on Hubble. We have about 500 people here who all are very proud to have been part of the Hubble program. So no matter what you do in your career, you can be an artist and still be involved in science. I'm an astronomer, but I've worked on 3 IMAX films. So really, you don't need to limit yourself in your career, and we embody that here at the Space Telescope Science Institute. So let's talk about Hubble. Hubble is a space telescope. Space is its middle name. And here is an image of Earth, and it's not that far out into space. Here is a diagram showing you the size of Hubble's orbit relative to the size of Earth. Hubble is in what we call low Earth orbit. It's just up above Earth's atmosphere. Here's an image that illustrates that. Hubble is just above Earth's atmosphere. And if you look, you can see that fuzzy edge to Earth's atmosphere. That is Hubble's main advantage. By getting up above Earth's atmosphere, Hubble gets the clearest view of any visible light telescope. Now, when we were young, we all learned about Twinkle, Twinkle, Little Star. Well, that twinkle is caused by Earth's atmosphere. So it is the process of getting above Earth's atmosphere that gives Hubble its amazing views. Now, you don't need to read all of this slide. This is just some facts about Hubble, but you might want to know its size. Its length is about 43 feet, and that's the size of a large school bus. I like to sort of joke that if Ms. Frizzle in the Magic School Bus went up to visit Hubble, it'd be about the same size. Of course, those of you who've read the books recognize that Ms. Frizzle drives a shorter school bus. She'd have to drive one of the big, long school buses, and then it would be about the same size as Hubble. The other thing to note is that Hubble is moving at about 17,000 miles an hour and makes one orbit at about an hour and a half. So while we're doing this teach-in for about an hour, Hubble will travel around 2/3 of the way around Earth. The Hubble Space Telescope was launched in 1990, 25 years ago today. And do you know what NASA Administrator Charles Bolden was doing then? He was on the astronaut team that put Hubble into orbit. And here is a marvelous photograph of Hubble being set into orbit from the bay of the space shuttle. Now, 25 years ago is a really long time. Matter of fact, for all the kids that are in elementary school and middle school and high school and even college, 25 years is longer than they've been alive. Hubble was launched before you were born. You've never known a world without Hubble. So let's try and do an idea of what it was like way back in 1990. So this is an image of a computer that's very much like the one I had in 1990. For the adults, it's like a 386 with a CD-ROM drive and a 3.5-inch floppy disk. Now I have a computer that's 1,000 times faster, it has 1,000 times more memory, and it fits in my pocket. My cell phone that I carry today is 1,000 times better in every way than the computer I had in 1990. And it's probably 1,000,000 times more useful because of all the software that's written for it. Now, because of that, because it was so long ago in technology time, people may think that Hubble is old technology. Well, how do we keep it current? The astronauts who put Hubble not only put Hubble into orbit, they also went up and had 5 servicing missions to Hubble. Here are the pictures of the astronauts and some pictures of them servicing Hubble during those 5 servicing missions. Like that old computer, which I was able to upgrade the processor and upgrade the RAM and go from a CD-ROM drive to a DVD-ROM drive, we've been able to do that with Hubble. We've been able to take out the old instruments, put in new instruments, upgrade it, repair it, and as NASA likes to say, repair, refresh, and renew Hubble with each visit. So Hubble isn't old technology. Hubble is 25 years old since it was launched, but it is filled with a lot of brand new technology, and I'll show you the results of that. Now, it was really great that Hubble was able to be serviced because, and you don't remember this, again, this probably happened before you were born, but when Hubble was originally launched, it had a flaw in the mirror. The mirror was ground to a very exact shape, but it was just slightly out of focus. So on the left, you see the image of the center of a galaxy before the repair. In 1993, Servicing Mission 1 went up and repaired the flaw in Hubble's mirror. It basically put on eyeglasses on Hubble so that it could correct the wavefront so that Hubble could see clearly. On the right, you see the result after the repair. And you can see the clarity with which Hubble sees the universe. Now, that's not to say that before the repair, Hubble was useless. Hubble still had better resolution than any ground-based telescope before the repair and could still do science that could not be done from the ground. However, it was after the repair mission that Hubble was finally able to achieve its design specifications and do all the great science that we had intended it for. So let's talk about some of that science, and we'll begin in our solar system with the planet Jupiter. This is Jupiter, the largest of the planets, and it has a wonderful feature called the Great Red Spot. You can see it down there just below the equator. And if I zoom in on it, this isn't a zoom in, this is a picture from the Voyager mission that went past it. It's one of my favorite pictures in astronomy. There are so many of those. But you can see the Great Red Spot, and you can also see those white ovals, those large white ovals. These are all storms in Jupiter's atmosphere. Jupiter has a lot of storms, and those white ovals are storms like our giant hurricanes, and the Great Red Spot is the granddaddy of them all. It's the largest of the storms on Jupiter. How large is it? Well, here is a comparison of the Great Red Spot to our entire planet. On Jupiter, they have a storm larger than our entire planet. That's big. And not only is it big, but it's also long-lasting. Hubble has been up for 25 years and has studied the Great Red Spot for the entire 25 years. But the Great Red Spot has been around for as long as we know. We have observations from 200 years ago showing the Great Red Spot, and we may even have observations from 350 years ago showing the red spot. So it's a giant storm that lasts for centuries. Now, during Hubble's time watching it, Hubble has actually seen the Great Red Spot shrink. You can see in the top image, the Great Red Spot in 1995 was significantly larger than it is in the bottom image, the Great Red Spot in 2014. We've actually seen the Great Red Spots to shrink over the time Hubble has been up. Why? Well, I gotta be honest with you, we're not exactly sure. It's a topic of current research trying to find out why the Great Red Spot is very slowly shrinking over these past few decades. But there's more for red spots. Because in 1997, 3 of those white ovals that I mentioned earlier started to merge together. And in 1998, 2 of them merged. And in 2000, the 3 all merged together to form an oval that, well, I guess it's called oval BA. And that was the largest storm outside of the Great Red Spot on Jupiter. But in 2006, that oval turned red. And for the first time ever, we saw the formation of a red spot. Now, again, it's called oval BA, but we gave it the colloquial name Red Spot Junior. And Red Spot Junior has also proven to be a long-lived storm, and it is still there in Jupiter's atmosphere. Plus, in 2008, we saw the appearance of a 3rd red spot. So you've got the Great Red Spot on the right, Red Spot Junior down lower left, and in the middle on the left, we have what we colloquially called baby red spot. But you can see that Red Spot Junior is at a different latitude from the Great Red Spot. It has passed by the Great Red Spot several times, and everything's fine. Unfortunately, the baby red spot was at the same latitude, and so we watched over the summer of 2008 as it approached and then got caught into the vortices of the Great Red Spot and dissipated away. So with Hubble, we've been able to study the Great Red Spot over decades. We've seen the formation of Red Spot Junior, and we've seen the dissolution of the baby red spot. Now, next time you think that your weather is really horrible, just remember the storms here on Earth, they're nothing compared to what we have on Jupiter. So let's move on, we'll go up a scale to stars. And what we show here is the constellation of Orion. And the upper left star is a star called Betelgeuse. Now, what you need to remember about stars is that they're really, really far away. So when we look at a star, it's just a point of light. The size of a star compared to its distance is so great that even with the best telescopes, stars are just points of light. Except Hubble, with its exquisite resolution, was able to resolve the star Betelgeuse. It was able to measure several pixels across the face of Betelgeuse, the first time an optical telescope had been able to resolve a star. Now you might say, wow, Hubble is just so amazing. Well, it's also that Betelgeuse is so amazing because Betelgeuse is a red supergiant star. And you can see by the scale bars beneath it that Betelgeuse is not only larger than Earth's orbit, it's larger than Jupiter's orbit around the sun. So if Betelgeuse were in the place of our sun, Mercury, Venus, Earth, Mars, and Jupiter would all be orbiting inside of Betelgeuse. Another great use of Hubble for stars has been to look at star clusters. And this is the globular cluster Messier 80. And these are these really dense stellar systems, stars that formed all together and are orbiting around one another. And Hubble's exquisite resolution is especially good in looking toward the cores of these globular clusters and being able to resolve the individual stars and see the details of their characteristics and their motions within these globular clusters. Also, Hubble, being above Earth's atmosphere, can look in the ultraviolet, at the visible, and a little bit of the infrared. So this image here, with its bright red and bright blue colors, is actually showing you a multi-wavelength view of the interior of a globular cluster. The blue in this image is ultraviolet light, and the red in this image is infrared light. This shows that Hubble has been able to look in multi-wavelength from ultraviolet to visible to infrared inside this globular cluster. It also allows Hubble to capture the very rare objects within the globular cluster. For example, stars that have collided together and merged, these stellar collisions that occur only inside globular clusters, create blue stars that radiate in the ultraviolet. Or the old stars like Betelgeuse, the ones that are becoming red giants and supergiants, they will radiate a lot in the infrared and show up in the red. So Hubble has been very, very valuable in the study of these dense stellar systems and seeing how stars move and act in their characteristics inside star clusters. Now, star clusters are also very associated with nebulae. Matter of fact, stars form in clusters inside nebulae. And this image here is one that we released yesterday. For Hubble's 25th anniversary, we released an image of the star cluster Westerlund 2 inside the nebula GUM-29. And this is an image you may have seen on the internet in the last 24 hours because it's gotten quite a lot of attention. We also made a three-dimensional visualization of this where we get to fly in to take a look at that star cluster. Now, I can't show you the movies on this Hangout, but I can give you a few frames of it to give you a feeling of it. So the camera flies into the nebula GUM-29, and as we zoom in, the stars come past the camera, and the camera descends onto the edge of the nebula GUM-29, onto the lower rim of it. Then it starts to pass by a little veil of gas that's on the near edge of it and starts to penetrate into the heart of the nebula. We fly past all those pillars, these pillars of dark gas and dust that are pointed toward the cluster because they're actually being shaped by the cluster. The winds and radiation are shaping them. And finally, we zoom in to see the details of the thousands of stars inside the cluster Westerlund 2. This is a wonderful way to experience it, and it is our way of reminding you that these two-dimensional images from Hubble are really representations of a three-dimensional universe. Now, this is a great segue into talking about nebulae and a particular star formation region called the Orion Nebula. The Orion Nebula is one of the nearest large star-forming regions. It has all sorts of activity going on in it, and this image from 2006 is incredibly detailed. But actually, I'm going to go back to an image from 1995, which takes the center of the Orion Nebula and brings that out in sharp relief. In the center, there are four large stars called the trapezium. And it is these stars that have the strong stellar winds and the intense ultraviolet emission that cause the gas around it to glow and also shape the objects around it. For example, on the right in this image is a star called LL Orionis. And the winds from these hot stars in the center are sweeping past LL Orionis, and you can see a bow shock on its near side. A bow shock, like a boat going across a calm ocean, creates a bow shock in front of it. It's the same thing here, but now it's the winds from these stars sweeping past the gas around LL Orionis. In the upper left, I show you a star that's forming much nearer to the central cluster. And instead of just creating a nice soft bow shock, that bow shock has wrapped around to form a windsock type shape. We call these tadpoles, but actually astronomers give them the name proplyds for protoplanetary disks. What's happened is the wind is so strong, it has wrapped the gas around it and you get that windsock type shape. Finally, down bottom, you can see an image of a newborn star, and you can see a black area around it. That black area is a disk of material. And inside that disk of material, planets will be forming. In the Orion Nebula, we have now seen solar systems in formation. That star is born, and as that star is formed, you form a disk of material around it, and in that disk, you get planets. We can see planetary systems in formation in Orion. And Orion is very special to me because for the IMAX film Hubble 3D, we did a full-fledged 3D visualization of Orion. And I want to let you know that the IMAX company has re-released IMAX Hubble 3D in celebration of Hubble's 25th anniversary. So if you're looking for a way to get more Hubble this weekend, go out and check and see if your local IMAX theater is playing IMAX Hubble this weekend. Let's move on up to galaxies. And again, I have so many favorite images in astronomy. This is definitely one of them. The Whirlpool Galaxy. It's the classic spiral galaxy. You can see those beautiful pinwheel shape of those spiral arms. Now, to get a sense of scale for this galaxy, do you see all those pink dots along those spiral arms? Those pink regions are star-forming regions, like the Orion Nebula. Every single one. Matter of fact, Orion would probably be a pretty small one of those pink dots. All of those pink dots are places where thousands of stars are being born. And that gives you the scale that, there are hundreds of billions of stars in this galaxy. Now, spiral galaxies can also look like this one here, because spiral galaxies are actually pancake shaped. You see the spiral arms when you look at the pancake face on, but when you look at it edge on, you see that dark disk of material. Other galaxy shapes include a barred spiral shape, in which you've got a very long bar as well as the spiral arms. The spiral arms come off of the long bar in the center. If you just take that central region, which is sort of, fluffy shaped, you get an elliptical galaxy, which is spread out across filling volume. You could call it a football-shaped galaxy because they're never actually circular. They're always sort of an oblong football-like shape. Then, if you combine the two, if you take that elliptical galaxy in the center and you have the disk of the spiral, you get a shape called a lenticular galaxy. All right, this is the Sombrero Galaxy. You might be able to squint and be able to see the outline of Sombrero, but you can see it has that great big bulge as well as that disk. So these are the basic shapes of galaxies. And I don't want to claim that Hubble discovered them. They were discovered they were actually classified by Edwin Hubble, the namesake of the telescope. What Hubble has looked at are the different types of galaxies that go beyond this. So here are two galaxies. They're two spiral galaxies that appear to be interacting, but they're not. They're just passing by each other. One is overlapping. However, if they did interact, you might get galaxies that look like this. These two galaxies are called the mice. And you can see the center of the galaxies there, and then these long tidal tails. These tidal tails have been stretched off by the gravitational interaction between these galaxies. And Hubble has studied these galaxy interactions. And in particular, on the left, you see a ground-based image of a pair of galaxies called the antennae. Again, for those long tidal tails, looking like antennae sticking away from the center. And in the Hubble image on the right, you can see all those bright blue regions. These were observed in ultraviolet to find out the details of what's going on in the galaxy interaction. And we found that there were immense numbers of stars formed during these galaxy interactions. They formed these giant star clusters, bigger than we had imagined before, so big that the astronomer called them superstar clusters. So there are a lot of these galaxy interactions, and Hubble has studied a lot of them. This is our largest press release ever, when we had 59 images of galaxy interactions. And we can study galaxies that are coming together as they smash through each other, they develop their tidal tails, and come back and merge together. But Hubble had a really special press release concerning our own Milky Way galaxy. In the top left, you can see an image of our Milky Way galaxy as it looks today. And it is a spiral galaxy, but we're inside the spiral, so we see that edge-on view because we're inside that pancake. And in the background, you see a very small little galaxy. That's the nearest large galaxy called Andromeda. And Andromeda has been shown to be coming towards us. So in the top right, we have done a simulation of it. And you can see Andromeda is heading towards us. And the bottom left, you can see Andromeda getting even bigger. However, Hubble was able to measure the sideways motion of Andromeda to characterize the future collision between the Milky Way and Andromeda. And what Hubble was able to determine that no other telescope was able to do was that we are headed for a head-on collision. The Milky Way and Andromeda will collide in about 4 billion years. And that collision is shown in the lower right. Then we took it further. We followed it with a simulation to try and see how it would develop. And you can see in the upper left, lots of star formation happening during the collision. In the upper right, you can see the tidal tails stretching out. And in the lower left, you see the galaxies coming back together. And finally, in the lower right, you see that about 6 billion years from now, the Milky Way and Andromeda will actually merge together to become one galaxy. That is in our future. However, you don't really need to worry about it. Your kids won't see it. Your grandkids won't see it. Your great-great-great-great-great-great-great-grandkids won't see it because it's all going to happen about 4 billion years in the future. But I can say that I, as an astronomer, man, I'd really love to see that night sky during the collision. That'd be a sight to see. All right, so let's step up one more scale. Let's go out to the scale of the entire universe with this image, the Hubble Ultra Deep Field, or I'm just going to, for short, I'm going to call it the HUDF. Now, the Hubble Ultra Deep Field is the longest visible light exposure ever taken of the universe. It sees more galaxies and fainter galaxies, and thus galaxies at greater distances than any other visible light exposure ever taken. Let me zoom in on some of the details. So here are some of the details. And we can see we've got some big galaxies, we've got some medium galaxies, we've got some small galaxies. Now, I don't have to know exactly where these galaxies exist, but I can tell that the bigger galaxies, well, they're probably going to be more nearby. The medium-sized galaxies, they're going to be a little bit further away. And the small galaxies, well, they're going to be even more distant. So we're looking at galaxies stretched across the universe. One of the questions you might have, however, is, well, just how many galaxies are there? And this is where we bring up our nationwide galaxy count. So in preparation for this teach-in, we said, what can we do and involve the students in a science project during our national teach-in? So if you came to our teach-in page a couple weeks ago, you were able to participate in the nationwide galaxy count. And what we did is we took that Hubble Ultra Deep Field and we split it up into these small cutouts. And we asked people to go ahead and count galaxies in the cutouts and submit your numbers to us. And you did. We got a good number of responses, and we got a lot of variety in our responses. So this is the galaxy count distribution, and you can see it goes from 0 to 125 on the graph. The lowest we got was around 5, and the highest we got was a little over 120. So the same cutouts being counted by different people comes up with a variety of answers. Now you might say, oh, well, they got it right and they got it wrong. I would say that you all got it right, simply because we didn't tell you exactly what counted as a galaxy. We left that vague in the instructions, and matter of fact, we put it up to you to say you should look at it and you should try to determine what is a galaxy. As a matter of fact, we wanted you to work in teams, because this is a very important idea of science, that science isn't just coming up with the right answer. The right answer is not as important as the process of getting there. And so by working in a team and discussing with your team, well, this is what I think a galaxy should count as, or no, this is what I think a galaxy should count as, that is really the best process of science. It's that discussion in figuring out what you're after. That's really where the scientific insight takes place. Of course, everyone does want the answer. All right, so let me give you the answer, not from me as the astronomer, but from you, the folks who did the counting. So here is your answer. So in the HUDF galaxy counts, the average across all of the cutouts that people counted was 54.4 galaxies. So of these galaxies, of all the cutouts, the average number was 54. So first thing we want to do is estimate how many galaxies are in the entire HUDF. But how are we going to do that? What I need to tell you is that each of those cutouts was 1% of the HUDF. We divided the HUDF up into a 10 by 10 grid and asked you to count the cutouts, which were just one of those grid points. So if we are going to make an estimate of the number of galaxies in the HUDF, based on our average, we simply multiply by 100, and our estimate for the number of galaxies in the HUDF is 5,440. Really good estimate. Now, let's take it one step further. If the HUDF is a representative sample of the entire night sky, how many galaxies are there in the whole night sky? Again, you need to know what percentage the HUDF is of the whole night sky to get that answer. Let me show you. Here is the apparent size, here is the full moon, and the full moon on our night sky appears about half a degree across. The HUDF, by comparison, is only about 1/10 that size, okay? So the HUDF is small compared to the full moon as it appears from Earth. The full moon, although you might think it's awfully large, well, if you take a proper perspective view of it, it's actually pretty small because it's only half a degree across. And you remember there are 360 degrees in a circle, so half a degree in the night sky isn't all that big. So we're talking one factor in 720 in a circle, and then one factor in 10 from that. The answer is that there are 12,746,784 patches the same size as the HUDF across the entire night sky. The HUDF only represents 1/12 millionth of the entire night sky. So let's go back to our calculation. If we have 5,440 galaxies in the HUDF, and we multiply that by 12.7 million, your estimate of the entire number of galaxies in the entire universe is 69 billion. That's kind of cool. Just doing a counting exercise in your classroom, you can estimate the number of galaxies in the entire universe. When astronomers do it, we don't ask school kids to count our galaxies for us. We don't even ask our graduate students to do that. We ask our computers to do it. And so we have very sophisticated computer programs to identify the galaxies in images like this and count all of them for us. And so we can count all the galaxies in the HUDF, and the number we get is about 10,000. Now you should expect that your counting will of course be lower, simply because you can't see the very fine and faint pixels that a computer can see. But you did really well. And so if you take that 10,000 number in the HUDF, you can see that astronomers estimate that there are more than 100 billion galaxies in the entire universe. Now, if that were all the HUDF was about, it'd still be a really great image. But there is another story I want to tell you about it. And here, to illustrate that story, are some of the most distant objects in the Hubble Ultra Deep Field. And you can see they're not very exciting galaxies. They're faint red dots, small red things out at the furthest reaches of the universe. Now, let me tell you, why are they red? Well, they are red because the universe is expanding. And the light that travels across the expanding universe becomes stretched along with it. We call this cosmological redshift, because if you take short wavelengths and stretch them to longer wavelengths, for visible light, the blue is the shorter wavelengths, the red is the longer wavelengths, so the wavelengths stretch toward the red end of the spectrum. That's what cosmological redshift is, and that's why these galaxies appear red. They appear small because, well, this is a different story. A long time ago in a galaxy far, far away. Now, you may recognize that as the opening of Star Wars Episode 4. And it's actually one thing that George Lucas got right. Because when you are looking at a galaxy far, far away, you have to be looking at it a long time ago. Remember I talked about light traveling across space. It doesn't happen instantaneously. Light takes time to cross space. And for these most distant galaxies, it takes billions of years. So we're seeing these galaxies not as they are today, but as they were billions of years ago. Here's a diagram to illustrate that. At the bottom left, you can see some galaxies out to about 3 billion light years away. So we're seeing them as they were out to 3 billion years ago. And you can see those galaxies have the normal spiral shapes that we expect. In the center circle, we see galaxies from 3 to 7 billion light years away, so 3 to 7 billion years ago. And they also have spiral shapes, but they're not fully developed. You know, if the bottom ones are adult galaxies, these middle ones, maybe we'll call them teenager galaxies. And in the top right, you can see the galaxies that are red, and they're small, and they really don't have much spiral structure at all. They're still developing. These would be the kid galaxies. As we look out into space, we look back into time, and we can see the development of galaxies over time. And that is what makes the Hubble Ultra Deep Field so special, that not only do we see so many galaxies stretched across space, but also stretched across time, and we can see the history of the universe by looking deep with the Hubble Space Telescope. So we have shown you planets and stars and nebulae and galaxies, and we've taken you to the edge of the universe. Hubble, as a general purpose observatory, is able to study the complete sweep of the universe. And it's really our privilege to be able to bring this to you. Now, I know that you have some questions, and we asked you in advance to submit your questions. We got a whole bunch of questions. We chose 2 that we would answer live during the teach-in. So, the first question, what makes the pictures from Hubble so colorful? Because Hubble's images are just wonderfully compelling. I'm actually going to tell you a secret. It's not really a secret, but Hubble takes images that are always black and white. Every image Hubble takes is black and white. But what Hubble does is it takes images through filters. And so the image on the left goes through a red filter, the image in the center goes through a green filter, and the image on the right goes through a blue filter. And when they come down to us at Space Telescope, they are black and white. And we can add color to them so that we get red and green and blue to represent the colors that they've got. And then we combine them together, we get a full color image of, in this case, a galaxy. And in this galaxy, we have used these broadband red, green, and blue filters, just like the cones in your eye. You've got red, green, and blue cones in your eye. And so we call this sort of natural color, because it's kind of like what your eye would see if you had an eyeball as big as the Hubble Space Telescope's mirror. There are, however, most of Hubble observations are not taken in these broadband filters. For example, this image of a nebula was taken in the light of nitrogen emission, of hydrogen emission, and oxygen emission. These are 3 specific elements that radiate at specific wavelengths, and Hubble is able to filter out just that light, which is important to science. Now, both the nitrogen and the hydrogen outlines are in the red part of the spectrum, and the oxygen is more in the cyan portion of the spectrum. And if we combine them together, we would get an image like you see in the lower left. However, in that image, it's very hard to tell what is the nitrogen and what is the hydrogen. They're all sort of mixed together. So it's more scientifically useful, and I will say more beautiful, if instead we'd use nitrogen as red, hydrogen as green, and oxygen as blue. Combine those together, and you get the image in the lower right, which has a little bit more beauty to it, but it's also much more useful in being able to separate out the colors from the different emission of the different atoms. And that is what's useful scientifically. We call this representative color because we are representing each filter with a different color. And it's also what we do when we take images in the infrared and the ultraviolet, because what color is the ultraviolet? What color is the infrared? We need to take visible light colors to represent those. The point is that all of the images you see from Hubble, the data is real, but the colors, of course, sometimes have to represent other things that you can't see. The second question we're going to answer today is, what is the future of Hubble and space astronomy? Well, the future of Hubble is actually very bright. You might think that, oh, it's 25 years, it's getting toward the end of its life, this is a retrospective. No, actually, Hubble is doing really great. We have been really happy with the way the observatory has functioned since the last service mission in 2009. The folks here at Space Telescope have learned how to operate the batteries and the gyroscopes and do the observing in such ways that we are preserving and prolonging the life of the telescope. The Hubble is in many ways still at the peak of its powers, and we expect it to last at least another 5 years, and we're crossing our fingers and hoping that Hubble will last another 10 years. Yeah, we might be able to get 35 years out of this amazing telescope. Going beyond Hubble, we have a new great observatory from NASA called the James Webb Space Telescope. Now, the James Webb Space Telescope is the follow-on to Hubble, but it's a little different from Hubble. You can see it's got this giant mirror with this great big sunshade, and that's because it is an infrared observatory. It will be observing in infrared light. Why the infrared? Well, remember I talked about all those dust disks in Orion, and you want to look into those dark dust disks? Well, it's hard to, you can't see them using visible light. But infrared light with its longer wavelengths, as well as the radiation from the dust occurs in the infrared, allows the James Webb Space Telescope to look inside those dust disks and study star formation and planet formation with greater detail than Hubble could ever possibly do. Also, when we look out at those distant galaxies, the light that is stretched by cosmological redshift can be stretched past the visible light spectrum, can be stretched into the infrared and deep into the infrared. The HUDF runs out of galaxies after a while, not because the galaxies aren't there, but because Hubble can't see them. The light from those galaxies has been stretched to the infrared, and we need the James Webb Space Telescope in order to see these most distant and the earliest galaxies in the universe. So the James Webb Space Telescope is doing infrared observations. It will have the resolution of Hubble in the infrared and be able to do science that the Hubble Space Telescope was not able to do. Now, the James Webb Space Telescope doesn't launch until 2018. However, that doesn't mean you can't get involved with the James Webb Space Telescope now. And here to tell us about a project that you can do in your classroom is Jessica Kenny of the Space Telescope Science Institute.
Hello. Welcome to our Hangout. Again, I am Jessica Kinney, and I will be telling you about the James Webb STEM Innovation Project here at Space Telescope. This project was based upon the success of the 2009 Hubble Early Release Student Pilot Program. It's an interdisciplinary project where students are able to create and demonstrate their own ideas about the telescope. This project is implemented in 50 different states within the U.S. So this covers several disciplines. We have music, art, and writing. We have a few examples of some projects that students have completed. We have students who have completed this project by creating songs through music. We have students who have done a mural at their school that they devoted their summertime to create this mural with their parents, with their teachers, and with others in the community. We also have social studies students working with this project. And with world culture, they've studied how James Webb will impact the world and the other countries that have been involved in creating the telescope. We've had elementary school students who created this awesome JWST mirror segments. They recognize these patterns very similar to beehive patterns. And we have a few comments from teachers. This is a first grade teacher who felt like the students really were gaining thought-provoking questions related to the project. They developed skills and high-level comprehension from learning about the James Webb Space Telescope. We have a high school teacher who allowed their students to get real-world connections to the telescopes, and they did 3D models. They did songwriting, computer drawings related to James Webb. And here's just some inspiration from students who participated in this project, that they're really interested and they're hoping that they could go and take this opportunity to go in the future in their careers. So how do you want to get involved? How do you participate with us, to partner with us? We are able to give you resources, information from JWST scientists, and if you complete this project, you will receive a high quality, museum quality print for your classroom. And our contact information is John Maple. You will see it's jmaple@stsci.edu. And here is an image of the museum quality poster that you will receive upon completion of this project.
Fantastic.
Thanks.
And it's great that we're able to get the James Webb Space Telescope into classrooms 4 years, 5 years before its launch. So Hubble has been up for 25 years, and we are so excited that you chose to share it with us. But it's not over. There's a lot more. There's a lot more to come from Hubble, and we hope there's a lot more interaction that you can have with us here at Space Telescope Science Institute. We run what we call the Amazing Space Education Program. And if you want to see all the activities and you want to keep up perhaps with the future events we're going to do, come to our website, amazing-space.stsci.edu. Now I have to tell you, I think that website is going to undergo an upgrade over the summer. But by September, we will be able to, it'll be a new website, and we'll schedule some new events to do with teachers across the country. If you have questions or comments, I know we didn't answer all the questions. We got too many to answer. I tried to answer as many in my talk, but you can still send us questions or comments about this to amazing-space@stsci.edu. Finally, I know that we always go through these things much too quickly, and you might have missed something. All right, well, the recording will be available on YouTube very shortly afterwards, and also we will then put it up on TeacherTube early next week. I believe by Tuesday of next week, we'll have it up on TeacherTube, and guess what our username is there? It is Amazing Space, but this time without the hyphen. So on behalf of Bonnie Eisenhammer, the Office of Public Outreach, the Space Telescope Science Institute, and all of the folks at NASA who work on Hubble, thank you for celebrating Hubble's 25th anniversary with us, and keep exploring your universe. Hi, I'm Dr. Frank Summers of the Space Telescope Science Institute, and welcome to the Hubble National Teach-In. First, we've got a very special guest, NASA Administrator Charles Bolden, who wants to give you his own personal welcome.
Thank you to all the educators, students, scientists, and engineers participating in today's Hubble Teach-In. When we launched this magnificent telescope 25 years ago today, we knew it would be special, but we really had no idea the degree to which it would transform our understanding of the universe and rewrite textbooks. Today, the Hubble Space Telescope continues to provide more data each year than there is in the entire Library of Congress. It's confirmed the presence of black holes in the centers of the galaxy. It made the first observations of the chemical makeup of the atmosphere of a planet orbiting another star. It helped scientists determine that the cosmos is 13.7 billion years old. It provided the first high-resolution maps of the structures of planet-forming disks around stars like our sun. And those are just a few of Hubble's greatest hits. It was my great pleasure to be a part of the crew that brought Hubble to space. Many astronauts since have helped repair it and keep it running, and many talented and dedicated folks on the ground have continued to monitor and manage this magnificent one-of-a-kind telescope. There are nearly endless possibilities for learning from the wonderful data and images that Hubble continues to send us. I applaud the teach-in for helping to inspire the next generation of scientists and engineers who may someday work on their own great observatory and once again transform humanity's understanding of our place in the universe. I hope you learn a lot today. I also hope your journey with Hubble, the James Webb Space Telescope that launches in just a few years, and all of NASA's missions will continue to inspire you and help you make your own great leaps of discovery.
The public outreach here at STSCI. In particular, I want to give you a welcome from Bonnie Eisenhammer, our Education Program Manager. She's the one on the right in this image. Bonnie and I work very close together. We believe in the scientist-educator partnership, which is what makes our education program so special. We also have a lot of other folks here at the Space Telescope Science Institute. This is one of our group photographs we've taken when the astronauts come to visit. You can see that there are a lot of folks here. And it includes the people that you might normally expect, the astronomers, the engineers, the computer programmers that put Hubble into orbit. And here is a marvelous photograph of Hubble being set into orbit from the bay of the space shuttle. Now, 25 years ago is a really long time. Matter of fact, for all the kids that are in elementary school and middle school and high school and even college, 25 years is longer than they've been alive. Hubble was launched before you were born. You've never known a world without Hubble. So let's try and do an idea of what it was like way back in 1990. So this is an image of a computer that's very much like the one I had in 1990. For the adults, it's like a 386 with a CD-ROM drive and a 3.5-inch floppy disk. Now I have a computer that's 1,000 times faster, it has 1,000 times more memory, and it fits in my pocket. My cell phone that I carry today is 1,000 times better in every way than the computer I had in 1990. And it's probably 1,000,000 times more useful because of all the software that's written for it. Now, because of that, because it was so long ago in technology time, people may think that Hubble is old technology. Well, how do we keep it current? The astronauts who put Hubble into, not only, it also includes the people that you need to run a business, those who'd work in finance, personnel, maintenance, but it also includes some people you might not expect, like writers, artists, and teachers. These are the people that help us get Hubble's discoveries out to the public and out into our education. And I think for us, it teaches a lesson that you don't have to be a PhD astrophysics geek to work on Hubble. We have about 500 people here who all are very proud to have been part of the Hubble program. So no matter what you do in your career, you can be an artist and still be involved in science. I'm an astronomer, but I've worked on 3 IMAX films. So really, you don't need to limit yourself in your career, and we embody that here at the Space Telescope Science Institute. So let's talk about Hubble. Hubble is a space telescope. Space is its middle name. And here is an image of Earth, and it's not that far out into space. Here is a diagram showing you the size of Hubble's orbit relative to the size of Earth. Hubble is in what we call low Earth orbit. It's just up above Earth's atmosphere. Here's an image that illustrates that. Hubble is just above Earth's atmosphere. And if you look, you can see that fuzzy edge to Earth's atmosphere. That is Hubble's main advantage. By getting up above Earth's atmosphere, Hubble gets the clearest view of any visible light telescope. Now, when we were young, we all learned about twinkle, twinkle, little star. Well, that twinkle is caused by Earth's atmosphere. So it is the process of getting above Earth's atmosphere that gives Hubble its amazing views. Now, you don't need to read all of this slide. This is just some facts about Hubble, but you might want to know its size. Its length is about 43 feet, and that's the size of a large school bus. I like to sort of joke that if Ms. Frizzle and the Magic School Bus went up to visit Hubble, it'd be about the same size. Of course, those of you who've read the books recognize that Ms. Frizzle drives a shorter school bus. She'd have to drive one of the big, long school buses, and then it would be about the same size as Hubble. The other thing to note is that Hubble is moving at about 17,000 miles an hour and makes one orbit at about an hour and a half. So while we're doing this teach-in for about an hour, Hubble will travel around 2/3 of the way around Earth. The Hubble Space Telescope was launched in 1990, 25 years ago today. And do you know what NASA Administrator Charles Bolden was doing then? He was on the astronaut team